doop, doop. Pulling up slides. Oh yeah, I was supposed to upload these to Avenue, wasn't I? My goodness. There we go. Okay. My goodness, these people are going to deliver the thing they're going to deliver right as my lecture is starting, aren't they? Oh my goodness. Ugh. Alright. Well, anyway. Hello, class. Welcome, 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 welcome. If I step out of the stream for like a minute or two just to pull my package off the... Oh, wait, nope, they're pulling away. That's not for me. Okie dokie. Right. Anyway, hello. Thank you for the like, whoever just liked the video. I appreciate the likes. Anyway. Yeah, hello class. Welcome to your Thursday lecture for this week. We're going to continue to talk about strings, formatting, and file I/O. It's going to be a fun lecture. I hope everybody's strapped in, buckled in for this wild ride. Really quick, what's the best way to initialize an array of variables size to 0? Well, an array of size 0 doesn't just empty curly braces work? I'm pretty sure empty curly braces work. Give me a second here. Code, let's see. I'm just going to check if that's syntactically correct. Int x equals shaboom. Is this syntax correct? Ladies, do I have 3 numbers right? That's a reference to The Price is Right. What? Example.c. Unused variable x, but it seems to be fine. Yep. Yeah, so just empty curly braces will do her there. There you go. So, let's continue talking about strings and things. So, last time we had just finished talking about how to convert things to strings and from strings into various formats. And now we're going to talk about the string.h library, which contains a number of your essential operations over strings. Things like copying strings, comparing strings, and even tokenizing strings. These string functions follow a general form. We're going to do a few of them in detail as an example, and the idea is, like, we're not going to do every single function in string.h explicitly and in a great deal of detail, because once you've seen a couple of them, you can get a feel for how it works, and then you can just, apply that knowledge to the rest of them, and that's more or less how it works. Also, if you ever want to know how to use any particular function out of the string library, you just have to, look it up in the GCC documentation or any sort of documentation. Anyway, comic. Haha. Get it? He's supposed to be writing lines, but he wrote a program to write his lines for him. Yeah. Anyway. So, soliciting string copy to switch string spots. That's an alliteration. Have you ever wanted to copy a string? Well, string copy and string copy are the functions for you. So, we've got two functions. All of these functions can be found in string.h, by the way. String copy and string copy. Both take the string stored at S2 and copy it to S1. So you take S2 and you copy it into whatever S1 is. Note that this is a overwriting operation. The extra argument in string copy, size tn, is similar to the size parameter in SNPrintf, which you will hopefully remember from last class. String copy will copy at most n characters. This is an effective guard against buffer overflow, which, as we've demonstrated multiple times during the course of this course, buffer overflow is a thing that you, the programmer, have to think of. Unlike in Python, this is not a thing that's handled for you. This sort of makes string copy the safe version of string copy. Once again, you, the programmer, are responsible for ensuring that S1 is large enough to contain S2, and that n takes that the size of both the buffers you're working with and the n that you specify is large enough to take into account the null terminating character. Because, as we know, if you do something that leaves off the null terminating character, you will end up with many of these functions look for null termination as the stopping condition for the algorithm. So if they don't find a null character, they'll just continue into unallocated memory space and, sift through a bunch of garbage before eventually failing on a segfault, unless they actually find memory that's all zeros, in which case it stops there, but you still have a bunch of garbage. So it doesn't even reliably result in a segfault. Sometimes it just introduces garbage data. But yeah, so string copy without the n is one of those types of functions. It will go in S2 until such time as it hits a null character, then it terminates. And, of course, you want to make sure that S1 is at least as big as S2. So there you go. Here are some more functions. String cat stands for string concatenate, and string ncat, which is string concatenate. The difference between cat and ncat are, of course, the same as the differences between string copy and string copy, conceptually speaking. String cat, its usage is very, very similar to string copy. The only difference is string cat starts writing string 2 into string 1 at the point of string 1's null terminating character. So this is what concatenation means. If you were to draw an analogy to Python, a concatenation operation is, if you're unfamiliar with the term, in Python on strings is mapped to the plus sign. So that is a concatenation operation. And you can see where this null terminator would have been, that's where W goes, and then it continues on. Concatenation. We also have string error. which takes an integer, which is the error number. String error is an interesting one. It accepts an error number and finds your computer or your compiler's corresponding error message and then returns that. So, if you ever wanted to know what a -7 error was, you could have this function look that up for your particular system. And of course we have strlen, L-E-N. strlength accepts a string and produces the number of characters in it, null character excluded. So of course the issue with string length is, once again, it expects your string to be null terminated. So if you have somewhere messed the null termination property up, then string length is going to be another one of these things that dips into unallocated memory space. So yeah, string functions. These are cool. Oop, I got a question. Boop, boop, boop. This would have been useful in the last assignment. You will find that it is even more useful in the next assignment, because the next assignment is largely based on string operations. So there you go. Little preview of what the next assignment is going to be. Ooh, okay. Okay. Get your notepads ready, class, because this is the portion in the lecture where I give you hints about the test. Because we got a test coming up on Saturday, and you guys might be interested in, more specific information about what the coverage might be. What are some specific areas that I recommend you brushing up on before the test? So, here are some hints. Number one, there are going to be some knowledge questions on the test in the form of multiple choice questions. So, the sort of testable material includes all of the information that's in the slides, not just, the stuff that we've done in assignments. So, I think that it would be really good for you guys to know how compilers work. That's from slide deck 1. It would also be really good for you guys to know how the stack frame works. Or the call stack and stack frames. Stack frames go in the call stack. There you go. So it would be good for you guys to know how the system call stack works. Yep. I think that's it. It's kind of dumb having multiple choice questions on an open book test, in my opinion, but what are you going to do? It's a kind of an irreducible problem of the manner in which the courses are being done this semester. Yeah, anyway. So, these are functions. Have you ever needed to be able to tell if two strings are the same string? Then string comp is for you. String comparison. Oop, we've got a question. I know you've mentioned this, but just to clarify, will string formatting be on the test? No. The test covers up to the end of pointers. However, I highly recommend that you guys be familiar with pointers as well. One might even say that pointers might be considered to be somewhat disproportionately represented in the test. No pointers, no dynamic allocation. Be comfortable with like regular pointer operations like dereferencing and address of and that sort of thing. Oh man, I love that we've got memes I love that we've got memes. I didn't know that you could do video on this. This is really cool. I like that. Anyway, so, yeah. Anyway, so that's all the hints I'm giving. That's all the hints you get. Wow. So string comparison. It takes a constant string and it produces it takes two constant strings and it produces an integer. Now, string comparison function it's a function that vastly predates the existence of booleans as a type in C. Therefore, it kind of uses them in a manner that's dissimilar than you might expect for this type of test, which would normally occur inside of a like an if statement or something, right? The point of this is for control flow and being able to tell what something is, etc., etc. So this function returns 0 if the strings are the same string. It returns a value less than 0 if S1 is less than S, and it returns a value greater than 0 if S1 is greater than S2. So, and of course, the normal restriction applies for string n comparison, which adds an additional argument n, which is the stopping point of the comparison. So if you only want to compare this many characters, then you use n. So the question then becomes, why am I being so coy about the concept of less than and greater than with respect to strings? Well, that's because the ordering over strings that's used by default in C and, the standard library is a lexicographic ordering. So if you think about it, what's essentially happening is we are taking the strings one character at a time, comparing each of those characters, seeing if they're the same character. If they are the same character, then we move on to the next character. And if they're not the same character, we judge them based on their ASCII value to see whether or not one is higher than the other. This is an important thing to know because there are certain, consequences of that. ASCII table. Images. Is this going to be good enough? We'll see. This is going to be very small, but there we go. Maybe that's better. So this is the ASCII table, of course. For example, according to lexicographic ordering, the space character is before any of the alphabetic characters. Uppercase letters come before or are less than lowercase letters. So in a lexicographic ordering, if you were ordering like a series of strings according to lexicographic ordering, anything that had a capital would come before anything that had a lowercase. So you'd essentially have all of the strings starting with uppercase characters coming first, and then all of the ones coming with lowercase characters. So, for example, uppercase V is still considered smaller than lowercase k, even though according to like a dictionary's version of lexicographic ordering, k would definitely come before V. So that's the thing to keep in mind, is that we are ordering things based on their ASCII values. So, yeah, hopefully that's reasonably straightforward. Why constant strings? Good question. So you may have noticed that there are some strings which are constant here and some strings which are not as well. It's a safety feature. The standard library functions have built into them a certain degree of safety with respect to strings. So the idea is, when you're copying S2 into S1, you don't actually have to modify S2. Like, it's a copy operation, not a move operation, right? We're not deleting S2. We are, in fact, not modifying S2 in any way, shape, or form. We are only modifying S1. So that's why S1 is being, S1 is not a constant char, but S2 is. Similarly, with string concatenation, S1 is actually being modified, but S2 is not. So S1 is not a constant char, but S2 is. You'll notice with string length, we don't need to modify the string in order to read its length, right? We don't need write privileges to be able to do that, so we aren't given write privileges. Similarly, with string comparison, neither S1 nor S2 need to be modified by the comparison operation. All we need is the internet. All we need is the internet. All we need is the integer at the end, which tells us if the strings are less than, greater than, according to lexicographical ordering, or if they're the same. So they are constant chars. The standard library function is only permitting itself reading privileges, not read and write privileges. So there you go. So does it return the first difference in ASCII values for the two characters? I don't know. I don't know what the actual values are. It's possible. But I'd like to, you guys can test that on your own if you're curious. I'd like to keep the lecture moving, because I realized I've been looking at the course syllabus stuff, and the degree to which we have to actually cover C++ is actually there's not a huge amount of it that we have to cover in in either the course description or the reporting requirements to the PEO. We're supposed to sort of vaguely, in a hand-wavy kind of way, talk about modularization and classes, but you can do that in like 2 slides, you know? So I'd like to be able to give a little bit of a more robust description of C++, so if we keep this short, then that's good. Anyway, search, destroy, and tokenize. There are a bunch of other string.h functions, which we're not going to go through in a lot of depth, but we're going to, you should be aware of their existence. So, string char, I think that's how you interpret that, or string character, locates the first occurrence of character C in string S. If C is found, a pointer to C in S is returned. Otherwise, a null pointer is returned. So this is very similar to your Python index function. strcspan, not the political news channel or the government news channel, but cspan takes 2 constant character arrays, determines and returns the length of the initial segment of the string S consisting of characters not contained in string S2. So if you imagine S1 is some text out of a book, and string 2 is a collection of all of the punctuation marks, it would give you the length of the initial segment of S1 that doesn't have a punctuation mark. As soon as there's a punctuation mark, it chops it. It stops counting. I had a question. If some of the stuff we learned this week happens to be useful on the test, are we allowed to use it, or will the autograder not like it? As long as you're importing the correct libraries, you'll be fine. I don't think that you'll have much occasion to be using this stuff on the test, as I don't think characters or character manipulations or strings, I don't think there's a single string on the test, aside from, like, that's the way in which you will be entering your multiple choice answers, is as characters. Basically, for the multiple choice questions, you'll be given a bunch of functions that are returning, like, the character capital X, and you just have to replace the capital X with whatever answer you want in, like, A, B, C, or D. You know, so in that sense, you'll be using characters, but there's really not much to do with characters for the entire rest of the class, so, or the test. So I don't think you'll be needing this stuff for the test. But yes, in general, the general rule is you are permitted to use all of the programming tools at your disposal. You know, as long as it's not like cheating and not having to actually write the algorithm or something like that. I don't think that. Well, yeah, I should be careful saying things like I don't think anybody will be able to cheat the system, but my goodness. Anyway, yeah, you should not be limited. My general philosophy of programming is that programs are tools. Like, programming, like, functions are tools, right? It doesn't make sense for me to say to you, okay, now I want you to do this plumbing work, but you're not allowed to use this wrench, that wrench, or that wrench. You should be allowed the freedom to use whatever wrench you think is good for that particular plumbing situation. And that's also how I think about programming. Of course, that kind of necessarily advantages people who have already learned the language, but why wouldn't you... Why is it wrong for somebody who already knows C to be able to pass this class easily, you know? Anyway! String span. String S span determines the length of the interval of the initial segment of the string S consisting only of characters in the string S2. So whereas string C span was everything, you know, we are stopping at anything in S2. The next one is we're stopping at anything not in S2. strpbark, PBRK, locates the first occurrence in the string S1 of any characters in string S2. If a character from the string S2 is found, the pointer to the character is returned, otherwise a null pointer is returned. So this is a search. It's like a generalization of string string characters, string CHR, but instead of just taking a single character, you are taking a list of possible characters. I got a couple of questions. Can we use things that come from the header files like string reverse with reverses a string? I know strings aren't on the test here, but there are some built-in functions like this that might be helpful. Yes! Absolutely! Please. Can you use code that you wrote from the assignments? Yep. Yeah, you can do that too. Like, for example, if you wrote a quick little function that, like, prints out an array and you've been using that function in, like, all of your things to look at your arrays, you're absolutely welcome to use that as well. If some of the stuff we learned this week happens to... answered that already. Yep. Okay. Cool. So, string rchar locates the last occurrence of C in string S. So this is like search, but from the back instead of the front. We then have string, which locates the first occurrence in S1 of the string S2. If the string is found, the pointer to string in S1 is returned. Otherwise, a null pointer is returned. So, like in Python, half of these functions are the same function, but that's okay. String token is a very interesting one, though. It's kind of different. A sequence of calls to string token breaks S1 into tokens, or logical pieces such as words in a line of text, separated by characters contained in the string S2. The first call contains S1 as the first argument. The subsequent calls to continue tokenizing the same string contain null as the first argument. A pointer to the current token is returned by each call. If there are no more tokens when the function is called, null is returned. So, if you wanted to break up a string according to spaces to get the words out, string token is what you would be using. So, this is a handy little reference sheet for all of you people who already know Python of some functions from the C, some functions in C that we've been talking about over the last two sections of the slides, and their rough Python equivalents. So, string to L is roughly equivalent to int myString. SN_printf is roughly equivalent to string myInteger. String copy is roughly equivalent to copy.deepCopy. String cat is foo plus bar. String length is length foo. String comp is, in Python, that's mapped to equality, the inequality operators, etc., etc. String character is foo.indexBar, and string toke is roughly equivalent to foo.splitBar. However, in the case of split, of course, it generates a list of all of the individual strings that it broke up, whereas in string token you have to keep getting new pointers to the subsequent words by rerunning string token. So, there you go. Surely this is generalizable! So, given that in C, data types are as a concept, are somewhat ephemeral, it should be the case that the above operations on char stars should be reasonably generalizable. So the idea, the point I'm trying to make here is all of these functions are occurring on characters. Characters are really just 1 byte memory chunks, right? Why wouldn't we be able to have some of these operate over differently sized memory chunks? Because all that an integer is, as compared to a character, is a memory chunk that's 4 times the size of a character. In theory, we can operate on these things in the same manner. Enter the mem copy, or the mem functions. So, the big difference between string copy and mem copy, for example, is you'll notice that we are dealing here with void pointers rather than char pointers. Remember our rules about void pointers. A pointer of any data type may be assigned to a void pointer. That means that S1 and S2 in these instances can be composed of pointers to any data type. Similarly, this function returns a void pointer which may be cast to any data type. And while it is possible to mix and match your pointer types, hypothetically speaking, within the context of this this function, or these sets of functions, that would be considered irresponsible, and I would have to wag my finger at you. Generally speaking, when you're using these, you should be using consistent pointer types. Make them all ints, make them all long, make them all float, make them all whatever. Just make them consistent. And of course, the other thing to notice is that we are also specifying a size here, so the size specification of these functions operates in the same manner as string n copy, right? You are processing at most n bytes. The reason that you have to specify n in these cases is because we are no longer working on strings, we can no longer assume null termination, so there is no other stopping condition, right? So n has to be specified. So we've got memcopy, copies n bytes from the object pointed to by S2 into the object pointed to by S1. A pointer to the resulting object is returned. Memmove copies n bytes from the object pointed to by S1 into the object pointed to by S1. The copy is performed as if the bytes were first copied from the object pointed to by S2 into a temporary array, and then from the temporary array into the object pointed to by S1. A pointer to the resulting object is returned. I'm not sure why you would use that over memcopy. Probably there are reasons, but it's basically in here because I didn't want to remove it. Would have been too much work to remove it from like this PNG image. So memcomp, again, that's string comp, but it operates over a more general memory type. Memchr locates the first occurrence of C, converted to use unsigned char. So there you go. And memset. Memset is kind of interesting. It basically it writes C into the first n bytes of the object. So this is like a overwriting operation. Yeah. Anyway, there you go. Cool. So, we move from our discussion of string.h into a discussion of formatting. So, up to this point, we have only briefly touched on the advanced features of the formatting tag %sign. So this is the thing that we're doing with, like, printf. Like, you've been using this in printf this whole time, but there are some advanced features that you should know about. Ooh, I've got questions. Okay. What's size_t? That's a good question. So, size_t is, first of all, you may have noticed that size_t is used quite often in these when we are specifying the size of something, the size of an array. It is a system-dependent value which is set, basically, it's a value that is in your operating system that is the bit width of the array addressing. Like, it's the bit width of, pardon me. How to, let me think about this for a second, how to phrase it. There is a maximum allowable array size that is set by your operating system, right? It has to do with the word size of a memory address, right? So the maximum size of an array, if you take log base 2 of that, you'll get the number of bits that are needed to represent that maximum array size, right? That's the bit width of the data type defined by size t. All that, when you see size t, that's actually kind of a clue that what it's looking for is an array size. So, yeah, it's a system set parameter. It's a type defined in your operating system. So, anyway, let's discuss some of the features of the formatting tag. We can round floating point numbers and display specified number of decimal places. We can align columns of numbers. We can right and left justify outputs. Pardon me. Sorry, guys. We can write exponential formats for floating point numbers, and we can have fixed field widths for various data types. all of the format specifiers we are about to discuss are used in printf and scanf and their cousins, like SN_printf. Question? Thank you. So, format specifiers for integer formats. D you should be familiar with, that is signed decimal integer. I is also signed decimal integer. The I and D specifiers are different when used with scanf. O is unsigned octal integer. U is unsigned decimal integer. X, capital or lowercase, displays an unsigned hexadecimal integer. H, L, or LL are placed before any of the above in order to specify that we are indicating a short, long, or long integer, respectively. These are the length modifiers. So if you wish to display a long signed decimal integer, that would be LD. There you go. So, here is an example of printing integers in various ways. DI, DD for positive and negative. We'll see how these come out. Hexadecimals, U. What does an so there are a couple of interesting things here, although most of it is kind of like humdrum. Number one, I don't think you guys have seen L as a suffix yet. If you add L as a suffix to any integer literal, that converts it to being a long integer literal. So that is used to specify the format, or specify the data type of the literal. So there you go. You can also, incidentally, do this with floating points and doubles. Oh my gosh! There. I was running low on battery. Wouldn't that have been tragic for my laptop to die 10 minutes to the end of the lesson? Holy smoke. The other interesting thing is what happens if you interpret a negative number as an unsigned integer. So, the answer to that question, what happens, is we get this long number. So, we're going to get into this a little more in depth when we talk about bitwise operations, but negative numbers are stored in what's called 2's complement form. What this essentially, like in very rough terms, what this means is that so let's imagine we have an 8-bit integer, right? In unsigned 8-bit arithmetic, the maximum value is 255, right? Because 2 to the power of 8 is 256, but you got to include 0, so 255. For a signed 8-bit integer, your range is going from 127 to negative 127. So it basically shifts the frame down around 0. But it's not like they're just using the most significant bit to indicate positivity or negativity. What's actually happening is that the I hope I get this right, but the 255 in unsigned representation is negative 1 in signed representation, and we can actually do that. Code example, yes. Let's just comment all of this out quickly. Printf short int and I'm going to do this in hexadecimal. So because that's 2 bytes, we need FFFF, and if we interpret the same thing as a unsigned integer, short unsigned integer, what do we get? Oh, I forgot that friggin'. There. Yeah. So the maximum value of an unsigned integer is just, 2 to the power of however many bits it is minus 1. However, if you interpret that as a signed integer, that is the same as -1. So what is actually happening is for the negative numbers, if you are counting down, like it's like you're counting down from maximum to go negative. Have to recompile. There you go. So there you go. That's a rough introduction to 2's complement. So, let's talk about floating point numbers. Our format conversion specifier E, or capital E, displays floating point numbers in exponential notation. This is, roughly speaking, scientific notation, x times 10 to the power of y. F, or F, displays floating point in fixed point notation, which is to say, just a decimal place. G is interesting because it'll pick either E or F depending on the magnitude of F. Depending on the magnitude of the number you're trying to print. And, of course, if you place L before any floating point conversion specifier, you are then doing a long double rather than just a regular double. So there you go. For example, if we have these numbers and we wish to print in E format, this is how it ends up. You'll notice that because the number is reasonably large, in this case, I believe it's anything that's over 1,000 or over 10 to the 4 or something like that, it chooses to display it in exponential notation. And notice whether the E is lowercase or capital is determined by whether this E is lowercase or capital. So there you go. Oh, sorry, 6. So E and F show 6 digits of precision by default. F will always print at least 1 digit to the left of the decimal point. G will select E if the exponent would be greater than the specified precision, i.e. default 6, or less than -4, and F otherwise. G does not print trailing zeros. E and G display rounded values. F displays truncated values. Here's some random trivia for you. You can print the % character with, either should be removed there, with 2 % signs. Note that /% doesn't work. There you go. Any questions? Any questions? I'm not sure if we can cover much more. I think we may stop there for today. Are there any questions from anybody about anything? I will answer questions now. How many gex? I don't know that meme. And I know better than to Google a meme on stream. So I'll say 7. I can do it on my phone, though. Oh, man. Stop stealing memes from Reddit. No. Never. Oh, is that a Fallout reference? Ha. Okay. Loading image. Okay. Just keep in mind, guys, that anything that gets posted to the stream has to be, you know, non-offensive, right? Not that you guys have been posting anything offensive. It's just, you know, maybe I should just say that. Ha! It's funny. Cool. Anyway, alright, there don't seem to be any questions about the material. Keep in mind, folks, that we'll be having office hours in this channel at 1:30. So we'll if you would like, you can totally show up. Habam. Alright. Yeah, I guess if anybody has any questions, then, you know, talk to me in an hour about it. See you, folks.